Okay, so welcome to this first video of a series where we want to go through the first volume of the Landau Lifshitz books on mechanics. So if you don't know, I'll probably make a later video about this, but the Landau Lifshitz series is a very influential series of theoretical physics books, and they are, I would say, famously hard, and I want to see if I can make them a little more accessible by making some YouTube videos about them. So the very first part of the first book is called The Equations of Motion, and the first section in there is called Generalized Coordinates. So what are we going to talk about? Okay, so this section is mostly like definitions. The first definition is that of a particle. So what is a particle? A particle is an object whose dimensions are negligible when describing its motion. So by dimensions we mean like its size basically, and anything that it does internally. So maybe some examples are easiest. So I first give you a good example and then a counter example. So an object that is not a particle. So what is a particle? For example, if you look at the planets, but planets are quite big, so you need to look at the planets at a scale where they are very small, and it doesn't matter what they do internally. So this scale is, for example, their motion around the sun. So if you look at planets that move around the sun in their ellipses, that can be treated as a particle. However, if you look at planets rotating about their axes, that is not a particle. So you can think of a particle as a point. Okay, so a particle is something that in the problem that you're describing is so small, or is so comparably small, that you can think of it as a single idealized point. And a particle has several properties. One of them is its position. So that is there's a squirrel outside. Let's move on. So there, by the position of a particle, we mean, of course, its x, y, z coordinates in Cartesian. So that's what you think it is. Like x, y, and z here. Let's say the particle is over here. And then you can describe its position by these three coordinates relative to these three axes. This was drawn rather poorly. Anyway, and you usually bundle the coordinates into a vector, which is here called r. I'm not yet sure if I will put like small arrows or something over the vectors to mark that they are vectors. I think this will overload the notation too much, so I will not use it, I think, for now. Yes, so you have the position, and now you have the velocity. And the velocity is, of course, the time derivative of the position. So this is dr over dt, which we define as r dot. So throughout the lecture, I will use the standard notation of like dots for time derivatives, and more importantly, I will use the standard math notation of so if you have an equal sign with two dots, that means that the side with the two dots, so here this new symbol, is defined by the other side. So this has already been defined. This is like standard notation in everywhere. And this is a potentially new notation. I'll define it by the left-hand side. Okay. Then there's also the acceleration, which is another property of the particle. And this, of course, is the second derivative, dot dot, or the first derivative of the velocity, etc. And you could also define more, like you could define a word for the third derivative of the position, etc. But interestingly, we will not need it. And I will get back to that in a few minutes. Okay, now let's imagine we have several particles, and we want to define the position of a whole system of particles, n, let's say, particles, that needs 3 times n coordinates. So why 3 times n? 3 because there's 3 coordinates for every particle, and there's n number of particles. And this number 3n is what's called the number of degrees of freedom of the system. So the degrees of freedom of a system is the number of independent coordinates needed to uniquely define the position of the system. So every system has a potentially different number of degrees of freedom. Depends on the problem. And these coordinates need not be Cartesian. So they don't have to be x, y, z. They can also be, for example, spherical coordinates or cylindrical, or really any other system. Like these two are just because these symmetries are quite common, but you could have completely wild descriptions of the system. And as long as they can fully determine the position of the system, it's fine. So in this spirit, any collection of S quantities, where S is the number of degrees of freedom, So in these quantities, let's call them Q1 to Qs, that completely determine the position of the system. Are called generalized coordinates. Of that system. And their derivatives so Q1 dot, etc., S dot are called generalized velocities. Okay, now the last thing we want to discuss in this section is the question of what do we need to determine the mechanical state of a system. So what do we mean by that? Imagine we have a system of S particles and we know where every one of them is. So we know the position of each of them. So if we knew position of every particle at time, let's say t0, i.e. q of t0, where q is just the vector of all of these guys, of all of these coordinates. What happens then? We could actually not calculate the state at a later time. T1 bigger than T0, because we don't know the velocities. Like each of the particles could move at a different speed in a different direction and so on. And if we don't know that, then we could be very surprised 1 second later, you know. And we also don't know the accelerations, etc. So we could not do that because we don't know their velocities. And accelerations, because the velocities could also change, etc. And now here's an interesting thing, which the authors don't really go into very much. They just say something along the lines of it's an empirical fact, we know from experience, that if we know coordinates and velocities, at the same time, that is, so it doesn't really help us if we knew the velocities 2 hours ago and we know the positions now, of course. They have to be at the same time. Then we can, in principle at least, determine the state of the system at all later times. So what this means is, if we know q of t, which again is like, let's say t0, which is like q1 of t0 up to qs of t0, all of them put into a nice vector, and similarly q dot of t, which is the same with the velocities, then we can calculate the acceleration, for example. And we can also calculate higher things, but yeah. So, and this is totally not clear a priori, right? So it could be that the world is in such a way that we have to know all derivatives of the velocity, of the position. But for some reason, we don't. We don't need to. And now the big question is, of course, how can we calculate the acceleration from the velocity and the position. And this is done via the so-called equations of motion. And this is what we'll do in the next videos.